So for the second main part is about improved reliability of low-K dielectric using hBN as a couple layer. So after we fabricated the low-K dielectric from the SEM image as shown here, the surface appears to be very rough with many irregular shapes as shown here. And compared to the dense LTO, the surface has a surface roughness of 1.5 nanometer. Compared to the dense LTO, low-K dielectric has a surface roughness of 80 nanometer. So it is extremely higher than the value for the LTO. So we need to reduce this high value for the surface roughness. So we tried to use silicon nitride as a couple layer because silicon nitride is widely used in the material technology. So we deposited silicon nitride using CVD process. Silicon nitride appears to have accumulation regions on the low-K dielectric because of the air pores on the surface as shown here. And for even for a higher thickness, we still have accumulation on the surface. And measuring the surface roughness for different thickness of silicon nitride, the surface roughness is reduced, but it's not reduced too much. Even for a thickness of 40 nanometer for the silicon nitride, we have a surface roughness of 60 nanometer. So it is still very high. So this is not a logical choice for the couple layer. So the second thing that we try to do is to use hBN as a couple layer to reduce the surface roughness, because actually hBN has a 2D surface, and the mechanical strength is very high. The elastic modulus is in the range of 700 gigapascal. So using hBN on the surface will not have too much deformation, and it will keep the surface flat. So here is a summary of the fabrication steps to transfer hBN. So first we have the hBN on top of a copper foil, and we coat it with PMMA, and then we etch the copper foil, and we transfer the PMMA, the hBN with PMMA on the low-K dielectric, and then we remove the PMMA, leaving the hBN on top of the low-K dielectric. And here the SEM images for the low-K dielectric with hBN. Here is the cross-section image with here is the low-K with many cylindrical air pores, and on the top we have the hBN here. And for the top view, here is the surface of the low-K dielectric. It is very rough with many irregular shapes. And for the region with hBN, on the surface, it is very smooth. It does not have many circles as the region here for the low-K. And then a very important issue is adhesion between the hBN and the low-K dielectric, because if the adhesion is not strong enough, so later during the chemical mechanical polishing process, the hBN can be delaminated from the low-K dielectric. So we studied the adhesion forces between the hBN and low-K dielectric. The working principle is very easy, shown here. We use using AFM. We use a tip and approach the surface as shown here. And once the tip is becoming very close to the surface, it has some attraction forces, and it is connected to the surface. And this graph shows the force versus deflection curve. Here is for the approach. And then after connection with the surface, we exert a force to go far from the surface and disconnect this tip. And depending on the adhesion forces between the surface and the other region, we require a higher force to disconnect the tip, as shown here. So this value characterizes the adhesion forces between two surfaces. The higher this value, the higher the adhesion forces. So we compare the adhesion of low-K with hBN compared to silicon nitride with low-K. So here is a reference. We have silicon nitride with low-K dielectric. we found that the adhesion forces for hBN is higher than the silicon nitride with low K dielectric, and it is higher with a thicker hBN film, as shown here. And even hBN has a higher adhesion forces with low K dielectric, which is higher than the silicon nitride with dense LTO. This is due to many reasons, because of the good mechanical strength of the hBN and the chemical stability, and many reasons behind this. So as a conclusion here, we found that the adhesion forces is very strong, so no need to worry about this. So then we study the surface roughness of the hBN on top of low K. So here's a measuring principle. We use AFM to measure the deformation by exerting some force on the surface. And here is a 3D image for the deformation of hBN on low K. Just here to show two regions. It shows a deformation due to the air pores. So we measure the average deformation of the surface as a measurement for the surface roughness. So here is a 3D image for the hBN on top of low K. Here for different hBN thickness, we found that the surface appeared to be very smooth compared to the case with silicon nitride, and the deformation is very small, and this amount of deformation is getting smaller with a thicker hBN film, as shown here. And from this graph, we found that using one layer of hBN can reduce the surface roughness even much better than using a thick silicon nitride film. And with a thicker hBN film, we can have a smaller value for the surface roughness. And for 10 layers of hBN, we have a surface roughness of 5 nanometer, which is very good. It can achieve the purpose. As we said before, that it requires to be in the range of 5 to 10 nanometer. Here is an important issue. Using any thickness of hBN can reduce the surface roughness too much. And the issue is that hBN has a high dielectric constant. So if we use a very thick hBN film, it can increase the overall effective dielectric constant. So we try to compromise the two issues of surface roughness and dielectric constant. So for the lowest metal layers, we have a very thin dielectric layer. So we use a very thin hBN film, maybe 2 or 3 layers. It can be in the range of 1 nanometer. And for the outmost metal layers, we have a very fixed dielectric layer. So we can use a thicker hBN film for this layer, since the surface roughness is has the highest value in the outmost metal lines. And here, as a comparison for the hBN on top of low K compared to the dense LTO, and it appears that the hBN has a very smooth surface, similar to the case with dense LTO. So in summary, we try to reduce the surface roughness of low K, which is 80 nanometer. We've tried to use very thick silicon nitride, and the surface roughness is still very high. Using one layer hBN can reduce it too much compared to thick silicon nitride layer. And using a thicker hBN film, it can reduce the surface roughness even higher compared to using silicon nitride. So then we study another issue of the hydrophobicity. So since we have many cylindrical air pores in the low K dielectric, the moisture from the air can penetrate into these air pores, and it can increase the electric constant, because the electric constant of water is around 80, so it is very high. So measuring the hydrophobicity can characterize this issue, because if the surface is hydrophobic, so water cannot penetrate into the electric material, and if it is hydrophilic, so it means that the water can penetrate into the low K. So measuring the contact angle as a measurement for the hydrophobicity, we found that the surface of silicon nitride on low K is very hydrophilic, with a very small contact angle. Comparing to the dense LTO, it has a very high contact angle in the range of 53. After we deposit hBN, we found that the surface is hydrophobic for both cases, with a very high contact angle, even higher than the dense LTO. And using a thicker hBN film, it has a higher value for the contact angle. So no need to worry about this. Using any thickness of hBN can produce a hydrophobic surface and prevent moisture to penetrate into the locate. So in summary, we study using silicon nitride to reduce the surface roughness of low-K dielectric, and we study the adhesion forces between a cable layer and low-K dielectric, and we measure the surface roughness of hBN cap low-K dielectric, and we study the hydrophobicity of hBN cap layer and how hBN can improve the hydrophobicity of low-K dielectric. So then for the last part is about the integration of copper with hBN as a cable layer. So the first important thing to consider here is also the adhesion between hBN and copper, since we already measured the adhesion between hBN and low-K. So also it is here important, because if it's not strong, it can be delaminated during the chemical and mechanical polishing process. So we use the same method, and we found also that this adhesion forces is very strong between hBN and copper, and is also better than silicon nitride with copper. Then we study the copper diffusion into the dense LTO. So here we have LTO layer on top of a silicon wafer, and we use a cable diffusion barrier of silicon nitride or hBN, and then we deposit the copper on top of the cable layer. We use EDS spectroscopy to measure the copper diffusion into the LTO. We found that copper can penetrate too much into the LTO. It can diffuse into the whole LTO layer, and even it can reach the silicon wafer. So we study using a thicker silicon nitride film, how it improves this copper diffusion issue, how it reduces the penetration depth. We found that using a thick silicon nitride diffusion barrier can reduce the copper diffusion, but this is a very thick diffusion barrier, 40 nanometer. So then we study using hBN as a diffusion barrier, since hBN has a 2D film, and it can create an energy barrier for copper to diffuse into the LTO. So after we have done the spectroscopy, using one layer of hBN can reduce the copper penetration depth much better than using a thick layer of silicon nitride. And using 10 layers of hBN can prevent any copper to diffuse into the LTO, as shown here, because this window just represents the copper film, and beyond this point, no copper exists in the LTO or in the silicon region. And we borrow this study to show that using hBN can reduce the copper diffusion, because if copper can diffuse into the LTO, it can form a short path for the current and can reduce the time to failure. So using hBN as a diffusion barrier, it can increase the failure time compared to the case without hBN. So then we study the copper diffusion into the low-K dielectric. In this picture, it shows that after we deposit the copper on top of low-K dielectric using silicon nitride as a diffusion barrier, copper is diffused as accumulation regions, as shown here. So from this result, the copper can diffuse very easy into the low-K dielectric from the regions between these accumulation regions. And using the EDS spectroscopy, we found that copper diffusion is very serious. It is even more serious than in LTO because we have many air pores that can be regions for the diffusion of copper. And using a thicker silicon nitride, it cannot improve the copper diffusion. It cannot prevent the copper diffusion into the low-K dielectric. So then we study how hBN can prevent copper diffusion. So here is an image for the hBN on top of the low-K dielectric, and in this case, copper is deposited as a 2D film, as shown here, without accumulation compared to the silicon nitride case. And after we have done the spectroscopy, we found that copper diffusion is reduced too much compared to the thick silicon nitride case. And using a thicker hBN film, it can prevent the copper diffusion to diffuse into the low-K dielectric better than the one-layer hBN. So in summary, we studied here in this part about the adhesion force between hBN and copper. We also studied the hBN as how it works as a copper diffusion barrier for LTO. And also we studied copper diffusion into low-K dielectric and how hBN can prevent the copper diffusion and improve the failure time of low-K dielectric. So in conclusion, we have studied how to fabricate high quality and vertically aligned CNT to fabricate low-K dielectric, and also how to achieve a flat surface using hBN cap low-K dielectric to reduce the surface roughness. And we studied also the strong adhesion forces between hBN and low-K dielectric, and also between hBN and copper surface. And also we studied the hydrophobicity of the surface with hBN compared to the silicon nitride case. And finally, we studied how hBN can work as a diffusion barrier and prevent copper diffusion into LTO or low-K dielectric. And this is the end of my presentation.